I would like to thanks to the organizer to invite me to give a talk. For me, it's a good opportunity to learn to very many nice talk from yesterday. In particular, I think the topic of my talk is very related to the talk of Laurent Verhon and Françoise Verhon. So I can start for my talk at the from the some basic concept, and so well, here is my talk, the outline of my talk. First, I will give some the motivation of my talk about the singular Lane-Emden equation, and then we introduce some known result about the equation with Hardy-Leray potential, and also the third part is our main result about this talk is about the isolated singularities for fractional Lane-Emden equations. All right. So yesterday and today, Professor Wei-Hong and deep result on the Lane-Emden equations, and so this give me the many basic result. But for the complex of my talk, I will start some early result about this equation. So we consider the following linear equations, and the singularity means means the solution near this point is not bounded, and we have the basic result is for the p less than n over n minus 2, which is called the series exponent, and there is no result, no positive solutions for omega equal to the Rn minus 0. For example, this is due to the Bidot-Verhon and Bohozaev at the beginning of this center. And when the p is bigger than n over n minus 2, there exists always a solution, which we call the U infinity, is the constant times the module of x power minus 2 over p minus 1. Okay, we call this the slow decay solutions. So in this direction, we give a very short summary about the result on this type of solutions. So at the beginning of 80s, Pierre-Louis Lyons studied this problem, the equation 2,2, and for the case of p between 1 and n over n minus 2, the solution satisfies the equation with a term the k times delta 0 in the distribution sense, but here the domain is omega, is the whole domain omega. In this time, the k is non-negative. When the k is equal to 0, the singularity 0 is so-called removable. When the k positive, we have a really singularity at 0. Okay, but for k is bigger or equal to n over n minus 2, then the solution U belongs to LP, and is satisfied in the distribution sense minus Laplace U equal to U power P. And then we cannot see, in some sense, we cannot see the singularity for the power of or the Green's function of the domain. Okay, and then in this direction, there are many other solutions results from 80s, and the result Aviles, Gidas Sprague, and Cavalieri Gidas Sprague, etc. So I just pass this because this is all of these are very known, and in the other case, for example, for the case of with the absorbing absorbed term, like Professor Wei Hong taught and yesterday and today, there are also the classification of the singularities. So we have two cases: either U like to the power of the module of x of power -2 over p minus 1, or the ux is like the Green's function. So that means the module of x power of 2 minus n. Okay, then there are many generation from the result of Marie-Françoise Bidot and Wei Hong, etc. And like yesterday, Professor Wei Hong said, there are a huge of paper about this direction, this result, not only for this equation, but also for the equation like with the Green term. Okay. But in another hand, for this one, I mentioned this because we will use the function u L infinity. So if we have the with the term the absorbing term, and then we can have a series of solution depending on the value of C. Okay, so for example, for any C positive, there exists a unique solution UC, which satisfies as x go to 0, the absontic behavior of x, ux is like the Green function of the domain. And as t and C go to infinity, the limit of the UC is go to U infinity, which is the behavior as the slow decay solutions for the whole space. Okay. And for this one, the linearized operator at U infinity is the operator of the Hardy type. Okay, so and this one is connected to our result. Okay, so for the linearized operator at U infinity, we get an operator of the Hardy type. Okay. And I just did some other result about this one because yesterday Ye Dong talk about the Hardy relation inequality, and there are many applications about this according to the power P, which which is compared with the best constant of Hardy inequality, and this were another direction from for example the stability of the extreme solution, etc. And there are also other recently there are also many results concerning this stability of solutions. I think Professor Zhang Yi also will talk about this. So this is about the the basic result from this. So the second part, we will talk about the non-homogeneous elliptical equations with the Hardy layer of potential. So for this operator, it's just like we talked, is the L mu equal to minus Laplace plus mu over modulo of x squared. And for mu is bigger or equal to mu 0, which is the best constant of the Hardy inequality. So the 0 belongs to the domain omega. If we consider the equation for in the whole space minus 0, just like the operator minus Laplace, we can consider the solution, the radial solution for this equation 3.5. And we can find, in this case, there exist the two branch of radial fundamental solutions. We write as phi the mu and the gamma the mu. Okay, and here there are two constants, the tau minus and the tau plus. They are the zeros of point of the equation of the equation mu minus tau times tau plus and minus 2. Okay, so these two equations satisfy the equation L the mu, the u equal to 0 in the whole space minus 0. In the sense, point wisely, of course, and in another way, the singularity of the 0 for these two functions is not, of course, is not the same. We can have the following result with Hu Yuan and Quartz, Alexander Quartz. So the first of all, we have this result that is the equation. First of all, we take the d mu. I think here the d mu is the gamma mu dx, and the theorem says that. I'm sorry. Okay. Hello.
No problem. We can hear very clear.
Okay. So for this theorem says that in fact we have L the mu, the phi equal to 0 in d prime Rn. Okay. So this is in this sense, and I'm sorry, this is the phi mu for equal to 0. Okay. No, I'm sorry. This is the one. But if we with this d mu, then we have in fact L the mu phi mu equal to c mu delta 0. Okay. 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 So this one that means the phi in the for this operator L the mu we can if we use changing the measure of dx to the d mu, then we have get in some sense we refine the singularity of the function phi in 0. Okay. And then we have studied the linear problem L the mu u if equal to f u equals 0 on the boundary, and we have make a connection to the weak solution of the solution of the equation 3.11. That means L mu the U equal to F plus C mu K times delta zero. That means in the this is I think this is in this one, okay. In this sense, we have in the sense of d mu distribution sense, we then get the solution of this equation to the above one, okay. And there are many other applications for these equations. For the existence or non-existence or the uniqueness of this equation, we have the following theorem. Okay, so let f be the function in c gamma the log the omega bar minus 0, and if we suppose the integral of modulo of f d mu is finite, then for any k belongs to R, the above equation has a unique weak solutions UK. It is a classical solution of 3.10. If we assume more that f, the limit of f times modulo of the 2 minus tau minus as x go to 0 equal to 0, then we have the behavior of the solution near the singularity 0 is like the function phi the mu. Okay. If the limit of this integral is infinity for the f is non-negative, then the problem has no negative solutions. So this gives us some greater view for the existence of solutions or not. And apply this, we can get some result about the generation of the Lyon's result. And also we can study the problem like when the singularity on the boundary. This is was published on the journal PAFA with also Chen and Quartz. And also we have some application for some linear system. Okay, this is for the equation with Hardy potential. Okay, now we can state our main results about the fractional Lane-Emden equations. Okay, so this is the problem we consider. So the main result is about the classification of the isolated singularity for positive solutions of the fractional Lane-Emden equations. So we have here the minus power s, the u equal to modulo of the theta u power p in b1 minus 0, and the u equal to h in outside of the ball, unit ball. And here we suppose the p is big than n plus theta over n minus 2s. Okay, this is we called the Seren's super critical case. H is a non-negative Holder continuous function in Rn minus B1. Okay, the minus the Laplace the S is the fractional Laplacian defined by the integration term. Okay. Which is a standard definition, and the constant CNS is normalized constant for the operator. Okay, so we will study the behavior of the solution near zero, and this we call the classification. But before state our results, I want to mention two recent results of Zhou Wenming and Wei Juncheng. They also studied this one. So first of all, I will mention the result of Hui Yang and Zhou Wenming. It is appeared in the Annales Yashbe. For this, the same equation, but here we use the symbol, the sigma, and their result is the following. For P belongs to n over n minus 2 sigma, and n plus 2 sigma over n minus 2 sigma, either the singularity 0 is removable, or we have the ux is like the c times modulo of x power minus 2 sigma over p minus 1. So here is the, we have here just no term, the modulo of x power theta. Okay, so this is the result of Zhou, and they use the standard methods to transform the non-local problem to a local problem, using the methods of like Cavallari and Sylvester. Okay, so they change to a near the point near zero to a half space, etc. Okay, and there are another result of Wei Juncheng and Wu Ke. It's about the same equation. For the power is exactly the series exponent, that is the n over n minus 2 sigma. And the result is that he can get the classification of the solutions about the singularity, like a term of modulo of x 2 sigma minus n and times minus log in the modulo x the power of n minus 2 sigma over 2 sigma. Okay, so Wei and his cooperator Wu Ke consider the critical series exponent case. Okay, of course there are also another result about the singular fractional Yamabe problem in conform geometry, and they consider the power, the critical power for that is the n plus 2s over n minus 2s, but the singular set is a submanifold of dimension n minus 2s over 2. So there are also a lot of results about the classification for the fractional Lane-Emden equations. So our result is about can be stated as the following. So we take H belongs to Cn minus B1, and also belongs to L1. I call it here is the L1, the S, the Rn for the simplification of notation. So this is the by the definition or for the fractional operator. According to the fractional operator, we need this content, and we suppose the theta equal to 0 or positive in the first statement. Okay, so when the theta is equal to 0, we suppose P is in the subcritical case for the Sobolev exponent. So it belongs to n over n minus 2s and n plus 2s over n minus 2s. And for theta bigger than 0, then p is bigger than n plus theta over n minus 2s. Okay, so we suppose u0 is a positive solutions of the equation. Then u0 has either removable singularity at 0, or we have the following that is in this term. So the limit of the u0 x times modulo of x power 2s plus theta over p minus 1, the limit inf and or the limit sup can be controlled by the kappa of p theta in this form, where the c0 is constant from Harnack inequality. Okay, so for example, here is the for the kappa the p theta is bigger than the limit inf and less than the limit sup. Okay, this is for the case this is theta. Okay, and when the theta is negative, we need some more other conditions, or when theta is 0, we for the p is supercritical for the Sobolev exponent, then we need some other conditions. That is, we suppose the h is a radially symmetric decreasing function defined on Rn minus B1 is a non-negative function, and is symmetric and is a Holder continuous on B2 minus B1. Okay, then for these two cases, if U0 is a positive solutions of of this equation, and if we have this condition, that means the U0, the inf of U0, when the x belongs to B1 minus 0 equal to h to 1, then the same conclusion still holds for U0. Okay, so this is the case when for theta equal to 0, but p is supercritical, or theta is negative, then p bigger than this one. In this case, we cannot have the same conclusion without additional condition for h. Okay, so this is our two main results about the singularity, the classification of the singularity for the fractional Lane-Emden equations. Okay. So we will explain what is the constant kappa pc theta. Okay, so first of all, for any tau belongs to minus n and 2s, we define the constant cs, the tau, for the using the function gamma, and this function cs is a positive when tau belongs to this interval that is the from 2s minus n to 0, and this function cs has has 2 0 at this end of the interval, that is at the 0 and the 2s minus n. Okay, the function is strict concave and uniquely has a maximum at the point 2s minus n over 2. this function has some, in fact, has some symmetry properties respected to the line 2s minus n over 2. Okay, so this is the property is this one, and the limits of the function cs of tau when tau go to minus n, and when the tau go to 2s is minus infinity. Another property for this function is that if we consider, we take the function, this is the x, okay, the modulo of x, the tau, then we have this one for any x different to 0. Okay, so this has this property, and now the kappa of p theta is just the function, the cs of minus 2s plus theta over p minus 1, and of power 1 over p minus 1. Okay, so we define this constant kappa p theta for p bigger than n plus theta over n minus 2s, and for theta bigger than minus 2s. We will solve our, we will take the classification using the operator, fractional Hardy operator. So we have, in fact, the connection for the fractional Hardy operator. Of course, this fractional Hardy operator is a generation for the usual Hardy operator. So the first term is changed to the minus Laplace power s, and the second one is the power of x is over 2s, and the mu is bigger than mu 0. We still take as mu 0, and it depends on the s, and you define by the function gamma. And Chen and West in the 3 years ago show that they study, in fact, this operator and give many useful properties for this one, and like the usual Hardy operator, they study give the fundamental solutions for this equation, L the mu s the u in the whole space minus 0, and they also exist the 2 branch of fundamental solutions for this operator. We still denote by gamma the mu, and the phi the mu, and the gamma the mu. Here the power is tau minus mu and tau plus mu. But in this case, we cannot have the explicit formula for the tau minus mu and the tau plus mu. We just have some relationship for this one. That is the tau minus mu plus tau plus the tau plus mu equal to 2s minus n. So this is just like the for s equal to 1, and for some special value we have the we can get the tau minus and the tau plus. Okay, so they give us all the description of this constant tau minus and tau plus for the fractional operator case. Okay, and then they study also the linear problem, but for the fractional Hardy problem, the L the mu s the u equal to f, and the u equal to h outside of the ball, and they also get the existence result and the non-existence and the result about this equation. Okay. But in this case, the problem is more, of course, is more complicated, even for the dual of the operator. So the dual is a weighted fractional Laplacian, and they not by this minus Laplace gamma mu the s. But in some sense, we can follow the idea for the case of when the s equal to 1. Okay, so we can get again some similar formula for the result, and in this case we need also the comparison principle for this operator, etc. So before give some state idea of the proof, I want to summarize the result, and we to get some clear picture here. So the key point is to get the up bound estimate for U0, just like this type of problem. So this is U0 less or equal to the C times modulo of X power of minus 2s plus theta over P minus 1. This is we need to get it. And for this one, we need to distinguish many different cases. For example, here, when the theta equal to 0, then we and the P belong between the n over n minus 2s and the n plus 2s over n minus 2s. That is when P is in the subcritical case. Then we can using the blow up technique to get this estimate. But when P is in the supercritical case, we cannot get this one, and we need to have some symmetry properties, and also to need this info. Suppose the info of U0 is exactly the value of H1, when the H, of course, H is symmetry, okay? And in fact, this is sufficient and necessary condition to have this for this case. But for the theta is positive, then we can get this estimate for all P bigger than n plus theta over n minus 2s. So we use only the blowing up technique to get this one. Okay, when the theta is negative, then we cannot use using the blow up technique. We still again using, or we still suppose that H is a symmetry, and we have the info of the U0 equal to H1 for this. And in this case, then we can get the U0 is controlled by this the modulo of X minus etc. Okay. Okay. I think for the classification, we also need to distinguish the case when the P is less than the term n plus 2s plus 2 theta over n minus 2s, and when the n when the p is bigger than this value, special value. Okay, because the singularity at 0 has a different straightness, so we need to take this different case. Okay, so Hu Yuan, Hu Yuan,
Yes,
yeah.
yes.
How many time I have?
No problem, because we start some time, some minutes later, so we can maybe 10 minutes, more or less.
10 minutes. Okay, I will finish in 10 minutes. Okay, thank you. So so in this case, we can prove this one. Okay, so I will give some idea. In particular, I will prove for the case theta is positive and 0 or positive, and we how to get the estimate for this one, and how to connect it to the fractional Hardy operator to get this to get the classification results. Okay. So so we will get the upper bounds for the case theta is which is non-negative. Okay, this one is the condition. Okay, so we have two cases, or this first one, or theta is positive and the p is bigger than n plus theta over n minus 2s. Okay, for the using the blowing up technique, we should the technique is very standard. For example, we can follow using the for example the work of Yan Li, etc. So we need to define the domain omega k, and also take the value x the k, and we define some function, the solution wk, and the wk will satisfy in this equation. Okay, then we need to have get some estimate for wk in the L1 s the Rn, but here we need to have some uniform bound for this. That is, the C is independent of k. So we're using integral upper bound. I will give the more precise statement later. Then we use take the as k go to infinity, it will go to some function w the infinity. Of course, this is up to a subsequence, and this is take in c log of 2s plus alpha prime, or and in the L1s, and the function w infinity is a positive and a bounded function. And for theta equal to 0, u w the infinity is a classical solution of this equation, which is bounded positive, and when the p belongs to this term, in this interval, there are no bounded positive solutions. It's known result. When the theta is positive, we can also get some contradiction. That is, we suppose we don't have this estimator. So wk is a uniform bound in this one, and we will get we will compare wk and the solution of this equation, the omega the k delta in B1, and the sigma is we choose some epsilon small, and we can compare the value of w0 and omega the k delta 0, and this is go to infinity, using the representation of the solution for omega k. and the reason is that this value go to infinity when k goes to infinity. Okay, this is some main step for this for proving that. Okay, and the key point for get the above case, that is in this one. Okay, in this estimate. Okay, is the following. So this is our key point. One of key point for get this one. We suppose P is big or less or big or equal to n plus theta over n minus 2s, and U0 is a non-negative classical solutions. Then we have this one. Okay, it belongs to L1, the B1 with the weight, the rho s. The rho is the distance to the boundary, and we have for any r smaller than 1/2, the integral of this term with the dx is less than with this power. Okay, so this is a very important, and for the above estimate. Okay, and then for a few minutes later, I will give the proof of some idea of the proof for the classification of isolate singularities. Of course, this is again for theta is non-negative, and is for P belongs to this term. When P is bigger than this one, we need to have another to take a more delicate estimate, or to distinguish the different case. Okay, we suppose U0 is a positive solution such that the limit that is 0 is a singular point. Okay, then we have this inequality. First of all, we record the kappa, the p theta is defined by the function cs, and the p belongs to this one is equivalent, in fact, to this power belongs to 2s minus n and 1/2 of this. Okay, so this is the value exactly we need. We should take attention to this one, and the tau minus of minus kappa, the p theta, the power p minus 1 is exactly this one, and type tau plus, so is given by this. Okay, so we suppose first kappa is the limit info of this quantity. Okay, we claim that the first claim is kappa is less or equal to kappa, the small k. I will call this small k. K is less or equal to kappa p theta. So by contradiction, if not, we suppose this is bigger than kappa of p theta, and we take epsilon 0 to this one, which is a positive, and the U0, then we can get is bigger than this one. Okay, so we first have the U0 and the U0 power p minus 1, etc. And we can take U0, we change the sign, we change in the point of view. We can consider this one is equal to some constant, okay, times U0 plus F1. The F1 is, of course, is equal to the right-hand side of the origin equation minus this one. Okay. so we need to get some estimate for F1. So this we change like this equation is like L the mu as the U0 equal to F1. Okay, and the mu is given by this one. Okay. So then we have some estimate. We need to have some estimate for F1. And this is F1 is bigger than this, can take this one. And we will take the mu, I just take this one is the mu p, maybe, okay. And then we have need to have the estimate for the mu p and the tau plus mu p, etc. And to get finally F1 is not belongs to L1 the BR0 with the measure of gamma, the use mu x. Okay. So we get a contradiction because this is we said from the result of Chen and West, we know this equation has no solutions. Okay. The second claim is if we take k to this one, we should prove that is bigger or less than kappa the C0. And this time, the equation is we change it in the same direction, in the same methods. We will get a equation like this one. And here the mu p, the theta is defined by this value, okay, by this value. And here we cannot have directly the result, don't like the claim one, but we need to have some lemma which is like some technique of bootstrap technique to get more and more estimate to have this. So if the tau one is positive, we have U0 is bounded, and this will give us the contradiction. If equal to 0, it is also, we can also get a contradiction. But if tau 1 is negative, we will again take it in the equation and using the lemma, some lemma we should to prove, and we can get a sequence of the tau n defined by this one, and their difference between the successive term is go to infinity, to get finally U0 should be bounded, and this will give a contradiction. Okay, so so I will stop here, and for the negative case for theta, it's needed to using the moving plane methods to get the estimate, etc. It's in some sense it's more complicated and too technique to have this one. I think I should stop here, and thanks again for the invitation, and thank you for very much.